Welcome to the deep dive. Today we are tackling what might be the single most crucial, high-stakes debate driving the next generation of AI. When we use reinforcement learning, that, optimization engine we strap onto our massive language models, are we actually teaching the model anything genuinely new? Or are we just, well, building a more efficient search engine for the smart answers it already kind of knew how to produce during pre-training?
That really is the million-dollar question, isn't it? Because how we answer it dictates, well, potentially billions in research and development resources down the line. And historically, we know RL can acquire new skills from scratch. You just have to think of things like AlphaGo or AlphaZero.
Right, learning Go and chess just from playing themselves.
Exactly. They learn to play at a world-class level purely through self-play and, crucially, outcome-based rewards. So that strongly suggests RL is this, profound mechanism for genuine skill acquisition.
But, and this is the tricky part, when you apply it to large language models, LLMs, models that have basically ingested half the internet, well, a highly credible, quite pessimistic view has popped up recently.
Work from people like you et al., Wu et al.
Yeah, suggesting that for a model like, say, GPT-4 or Llama, RL acts primarily as a powerful editor, maybe just re-ranking existing reasoning strategies the model already possessed.
They call this the re-ranking illusion, the idea being it's more about amplification of capabilities that were already latent, baked in during pre-training, rather than, true cognitive emergence of something brand new.
And this is precisely where our deep dive begins today. We are plunging into a really landmark study, I think, one designed explicitly to try and dismantle that re-ranking illusion.
That's right. The researchers constructed this very surgical, synthetic framework, a kind of clean test bed, if you will. The whole point was to rigorously test what they're calling the RL compositionality hypothesis, controlling for things like data contamination and complexity in a way that, frankly, you just can't do with messy real-world benchmarks.
Okay, so our mission today is to understand, really down to the nuts and bolts, the granular mechanical level, how LLMs might acquire genuinely new cognitive skills, specifically by composing existing sort of simpler skills, these atomic skills, much like, humans stack simple concepts together to tackle complex problems. Anderson talked about this way back in '82.
The idea of cognitive compositionality.
Exactly. We really want to know, if an LLM knows skill 5x's and it knows skill vexx, can RL actually teach it the new, totally unseen, and crucially systematic compositional skill 5x(x6 equals GFX? Can it truly master these nested dependencies? Okay, let's unpack this with extreme rigor, starting right at the beginning with the definitions and the framework itself.
Right. So the foundational challenge, the absolute first hurdle the researchers faced was contamination. It's a huge issue in LLM research.
Because if they used, say, common logic puzzles or described functions in plain English,
The LLM might just be recalling something it saw during pre-training. Could look like learning, but it's just memory retrieval. So to avoid this, they designed this whole system based on deductive reasoning, but applied to string transformations. Abstract strings.
okay, so building a clean test bed where success demands logical deduction, not just recalling some memorized factoid. And that meant they had to be incredibly precise about defining what a skill even means in this context.
Absolutely precise. Within the synthetic world, a skill is defined very simply. It's the ability to infer the output of a specific string transformation function. Let's call it phi(x) given some input string, $6. And they categorize these skills based on their complexity, their structure. First up, we have what they call atomic skills. Think of these as level 1 skills. These are single, non-decomposable transformations.
Right.
Like fun16x.
Just one step.
One step. They created 25 unique, distinct functions like this. They do things like, counting characters, filtering out vowels, compressing repeated letters, a whole set of basic building blocks. These are the fundamental knowledge units the model absolutely has to internalize first.
And then the second category, which is really the core focus of the study, compositional skills, level 2 and beyond.
Right. These are defined by the nesting depth. So level 2 means you've got a 2-function composition like ever and GX. An example might be func16, func15, ABC. And the difficulty level is controlled purely by this depth of nesting. Level dollar means you're composing one functions. This precise control over difficulty is absolutely critical for measuring generalization later on. You can really dial it up.
Let's double-click on that decontamination strategy, because this is where the rigor really shines, I think. You mentioned if the model had seen compress repeats a million times, it could cheat. How did they make sure the model was learning the function's logic from scratch right there in the experiment?
They did it by completely stripping out semantics. They didn't use descriptive names like compress repeats or remove vowels. Instead, they used these deliberately meaningless identifiers. Things like Fun 16, Funk 2, Funk 10, and so on.
Just labels.
Just labels. And crucially, the only time the model ever sees the underlying Python code definition, the def Fun 16 part, is during the first stage of training, stage 1. So if later on the model is just presented with the task Fun 16 some string, it has absolutely no prior association, no way to infer what Fun 16 actually does just from its name. It has to rely on what it learned in stage 1.
That guarantees these tasks are essentially unsolvable without the explicit controlled training they provide in the study. It really isolates the acquisition of those atomic skills purely to their training protocol. Very clean.
Exactly. It's a very elegant way to ensure you're measuring learning, not recall. Hashtag tag 1.2 example of atomic skill derivation.
Okay, so before we can even think about composing functions like FGUPL, the LLM has to absolutely nail the mechanical execution of a level 1 problem. An atomic skill. Let's focus on one, maybe Funk 16x, and walk through the detailed step-by-step logic the model must execute. I think this will give everyone listening a really solid mental model of what this foundational skill actually entails.
Good idea. So Fun 16 is defined, let's say, as the function that removes adjacent duplicate characters from a string S. You can kind of think of it as a compression operation, just make sure no character immediately repeats the one right before it. Let's trace an example. Input string, say this follows, ties this. We need to walk through the logic the LLM has to replicate, step by step, really rigorously.
Okay, dollars or recalers, what's the first step?
Well, the process is entirely algorithmic, right? First, there's the standard edge case check. If the input string S is empty, you just return S. But our string tie S isn't empty, so we proceed. The execution then requires initialization. The model has to start by creating, say, a result list, and it initializes it with the very first character of the input string, which is $50.
So result starts as just T.
Precisely. The model has now established a baseline, and from here it has to iterate through the rest of the input string, character by character.
Looking at IHBAAS.
Exactly. So step 3 is this iteration. We look at each character, let's call it C, in the substring middle dollars, which is indeed IHEAS, and the core logic, the heart of the function, is a conditional check at step 4. It's basically if a third proper result dax1 to result.append.
Okay, so in plain English,
Right.
only add the current character to our result list if it's different from the last character we successfully added.
That's it. So let's trace this for THIS. We need to detail what the model has to deduce at each iterative step.
Go.
Okay. First iteration, the character is I. The model checks. Is I different from the last character currently in result, which is T? Yes, I is not equal to T. So if it appends I, result is now TI.
Makes sense.
Next character, I. Is E different from the last result character? I. Yes. Append H result becomes TIIs.
Okay.
Character E. Is E different from E? Yes.
Okay.
Append result is TIE.
All right.
Character E is different from A. Yes, it is. Append's result is TIS.
All right.
Characters is. The first S. Is it
different
for
from
A?
A.
Yes, it is. Append's result is now TIHEIs.
And now the crucial one.
Character E is the second S. Here's the critical step where the condition fails. E is different from the last character added to result, which is also S. No, S is equal to S. The conditional check result 1 fails. So the model must not append this character. It has to correctly execute the skip logic here.
And that's the end of the string. So the final step is just joining the list back together.
Yeah. Exactly. Step 6 is basically join result, which takes TABT and turns it into the final output string. TIAS.
Okay. So the LLM has successfully inferred and, more importantly, executed the step-by-step logic of Funk 16. This level 1 execution is the absolute bedrock. If the model messes this up, well, composition is just impossible, right?
Completely impossible. This atomic mastery is the non-negotiable foundation. Hashtag tag 2. The 2-stage training protocol.
This level of rigor leads us perfectly into the training methodology they used. It's a 2-stage protocol run on a Llama 3.18b instruct base model, if I recall correctly. And the purpose of separating the training into 2 distinct stages seems really surgical. It's designed to isolate the effect of RL specifically on the compositional part of the skill, keeping it separate from learning the atomic part.
Precisely. Stage 1 is all about laying the groundwork, establishing the prerequisites. Its only goal is to make sure the model internalizes the behavior of all 25 of those unique atomic string transformation functions and does so to a really high degree of fidelity. And to achieve this, they used a technique called rejection fine-tuning, or RFT.
Okay, let's define RFT carefully here, because it's not quite the same as just standard supervised fine-tuning SFT, is it?
No, it's a bit more refined. RFT in this context involves first getting the model to generate many potential responses, or reasoning paths, for a given atomic problem. Then you filter those responses based on objective correctness. Did it produce the right final string? Did it follow a plausible step-by-step reasoning trajectory?
So you select the model's own successful attempts.
Exactly. And then you fine-tune the model using standard next token prediction, NTP, but only on those high-quality correct reasoning paths that the model itself generated. It essentially focuses the model's learning on reinforcing the successful strategies it already showed some inclination towards, rather than just copying an external oracle.
And this stage 1 is the only time the model gets to peek under the hood, right? The only time it sees the actual code.
That's the absolutely crucial detail here, yes. Stage 1 is the only stage where the models observe the explicit, complete Python function implementations, the actual def func16s.const. This is how the model definitively learns what that meaningless identifier func16 actually means in terms of logical steps. It connects the label to the logic. Without this step, the label is just noise.
They were also pretty clever about filtering the training data in this stage, weren't they? They generated something like 50,000 level 1 problems, but didn't just train on all of them blindly. Why filter?
Yeah, they optimized for learning efficiency, basically.
Yeah.
If the base llama model, even before RFT, already achieved 100% accuracy on a particular level 1 problem instance, well, training on that easy example probably doesn't teach it much new. It's diminishing returns.
Right, focus the training budget where it matters.
Yeah, exactly. So they discarded those trivial problems and focused the RFT process specifically on the non-trivial learning opportunities, the problems where the base model was initially struggling or getting it wrong. This focused refinement resulted in, I think, about 116,000 high-value training instances. It maximizes the model's foundational atomic knowledge before it ever encounters composition.
Okay, so stage 1 builds the atomic foundation. Stage 2 is where the real experiment happens. Now we have models that, in theory, know the rules for func2 and func16 individually, but now we test if they can chain them. And critically, the function definitions, the Python code, are completely hidden now.
Completely hidden. In stage 2, the model only sees compositions, like func2, func16x, along with the input x. It has to figure out the execution purely based on the structure and what it learned in stage 1. And this is where the crucial comparison comes in. They set up a few different training configurations in stage 2, but the most important contrast is between the mechanism of reinforcement learning, RL, versus the mechanism of rejection fine-tuning, RFT, when both are applied to the same set of compositional problems.
Okay, tell us about the RL setup first.
So for the online RL condition, they used a method called Group Relative Preference Optimization, or GRPO. It's known to be a pretty efficient RL algorithm for LLMs that basically tries to maximize the model's preference for generating better outcomes compared to worse ones. But the absolutely critical part here is the reward signal. The model only received binary rewards, a simple 1 for correct, 0 for incorrect, based only on whether the final output string matched the true answer.
Wait, let me pause you there because this is huge. Only pass-fail on the final output of, say, func16x.
That's it.
So it received no demonstrations of the intermediate steps, no hint that it should calculate func16x first, and then use that result.
Absolutely none. Zero intermediate supervision. It has to discover the entire internal execution strategy, the nested dependency, the sequential flow, purely from that incredibly sparse binary final outcome signal. It has to figure out how to get the right answer just by knowing if it got the right answer.
Wow. Okay. Now compare that to the RFT baseline in stage 2.
Right, the offline RFT baseline. This model was trained on the exact same set of compositional problems as the RL model. But instead of RL, it was trained using standard next token prediction, fine-tuning on complete, correct reasoning trajectories.
Meaning it saw the step-by-step solution, like step 1, compute func16x to get intermediate result. Step 2, compute func2 intermediate result to get final answer.
Exactly. This RFT model was essentially spoon-fed the correct reasoning path, including all the intermediate outputs provided by an external oracle, or a correct run of the code. Logically, you might think this full supervision, seeing the perfect breakdown, would be far superior for learning the compositional structure.
Seems intuitive, yeah. And they also tweaked the RL training data itself, didn't they, by level?
Yes, they had specific RL level configurations to really pinpoint where the compositional ability comes from and how it generalizes. These are important.
Yeah.
1. RL level 1. This model was trained in stage 2 using RL, but only on atomic level 1 tasks. It never saw a composition like FGX during RL training. This is the crucial control group. Does just getting better at atomic skills via RL spontaneously create compositionality? Spoiler, no.
Okay, control group.
RL level 2. This model was trained in stage 2 using RL, but only on 2-level compositions like FGX. This directly tests if the incentive provided by solving level 2 problems is enough to teach a general principle that extends to harder levels, level 3, 4, etc.
The core test case for compositional learning.
For RL level 1 plus 2. This model was trained in stage 2 using RL on a uniform mix of both atomic level 1 and 2-level composition level 2 tasks. The idea here is to ensure the model continuously reinforces both its foundational atomic skills and the emerging compositional skills simultaneously.
Okay, that sets the stage perfectly for the results later. We have atomic-only RL, compositional-only RL, and mixed RL, all compared against RFT on compositional data. Right, before we get to those results, though, let's really hammer home what the model is being asked to learn in stage 2, especially in that RL condition with only binary rewards. Let's walk through another level 2 problem, say y inserces f k x s x step by detailed step. I think we need to fully internalize the cognitive load here, the systematic execution it has to somehow discover.
Absolutely. Let's use the example where $5 is a func 2, which we'll say removes vowels, A, E, I, O, U.
Yeah.
And $8 is our old friend func 16, which compresses adjacent repeats. And we'll use the same input string as before. $6 is TSLs. So the specific problem the model sees is predict the output of vowels sun 16, TSS day. The LLM, without seeing the code, must somehow learn to systematically decompose this structure.
Okay. And the fundamental rule of compositionality or function nesting dictates that you have to resolve the deepest, innermost function first, right? You work from the inside out.
Precisely. So step 1 for the model is to resolve the inner function. That means it needs to compute func 16 to zeros. It has to recall the logic of func 16, remove adjacent duplicates, learn in stage 1, and apply it. As we derived earlier, this compresses the double S at the end. The intermediate output is the string tios. The LLM has to correctly calculate this intermediate string and essentially hold it in its context or internal state as a sequence of tokens.
Okay, intermediate result is TIHES. Now what?
Step 2 is that this intermediate string TIHES must now become the input to the outer function, full dollar. So the next computation the model must perform is IXDale, which translates to func 2, TIHES. It now needs to recall the logic for func 2, remove vowels from stage 1, and apply it to TIHES. The vowels in TIHES are I, E, and A.
So the model's task is to filter out I, E, and A from the string TIHES,
leaving just the consonants T, H, and S. And that brings us to step 3. The final output string is T, H, and H. What the LLM is learning in stage 2, especially the RL model, is how to systematically execute this sequential chain. It's not just predicting the final token as, it's learning to generate a token sequence that is the result of applying a sequence of functions, where the order and the dependencies are absolutely critical.
and it has to learn that entire inside-out procedure potentially just from pass-fail feedback on 3. That's the core challenge.
That's the core challenge and the potential magic of RL in this context. It's learning the abstract structure of how to compose. Tag 3. RL is the key to generalizable skill acquisition.
All right, the moment of truth. We have the setup, the definitions, the examples. Now for the first major reveal from the experimental data. Did that compositional training, especially the RL version, actually unlock generalized skill acquisition? Figure 2 in the paper seems to hold the answer, comparing that RL level 1 model, trained only on atomic skills in stage 2, against the RL level 2 and RL level 1 plus 2 models, which got the compositional incentives. What does it show? Hashtag tag 3.1, unlocking generalization.
Figure 2 is.
This figure 2 is really striking. First, let's look at that atomic-only model, RL level 1. It serves as our baseline for inherent compositionality. As expected, because it was trained with RL on level 1 tasks, it gets really good at them. It achieves high accuracy, somewhere around 90% on held-out level 1 test problems. So it definitely mastered the atomic skills even better with RL.
Okay, so RL sharpened its basic abilities.
Yes, but the critical finding is what happens when you test this model on composition. The moment you ask it to solve a level 2 problem, its performance just collapses. Its accuracy on level 2 tasks is consistently below 25%. Wow, so even though it's really good at 5x and Jokul individually, it can't put them together reliably at all.
Not reliably, no.
Yeah.
And it gets worse. When you test it on harder compositions, level 3, level 4, all the way up to level 6, its performance basically flatlines near 0 accuracy. Like 1-2% maybe, noise level.
Okay, that's a very clear result. Having robust atomic skills, even sharpened by RL, is absolutely not enough. The model doesn't spontaneously figure out the principle of function chaining just because it knows the building blocks really well.
Exactly. It proves that an explicit compositional incentive during training is required. You have to reward the model for actually doing the chaining. And that's exactly what you see with the other models. The learning curve is completely transformed when the model is trained on compositional data in stage 2. The model is trained specifically on level 2 problems, that's the RL level 2 model, and the RL level 1+2 model show a substantial improvement not just on level 2, but critically in generalizing to unseen, more difficult problems, levels 3, 4, 5, and 6, which they never saw examples of during training.
Okay, let's quantify that jump. How much better do they get on, say, level 3 problems, 3 nested functions totally unseen?
This is takeaway 1, the generalization power. On those level 3 tasks, accuracy jumps from that negligible maybe 5% score for the level 1 model up to a solid 30% for the compositionally trained RL models. That's a 6-fold increase on a task complexity they never explicitly trained for.
30% on 3 levels deep, learned from only seeing 2 levels deep. That's significant. What about even harder, level 4?
It continues. On level 4 problems, for nested functions, the compositionally trained models leap from, again, maybe 1% accuracy for the baseline up to around 15% accuracy.
15% might not sound amazing in absolute terms, but compared to near zero?
It's a massive relative improvement. It's a powerful demonstration that the models are not just memorizing the answers to the level 2 problems they saw in training. If they were just memorizing, performance on level 3 and 4 should be 0. Instead, they seem to have acquired a generalized principle for composing functions, a strategy that allows them to tackle compositions of arbitrary, unseen depth with significantly better than chance accuracy.
So this looks like strong validation for their hypothesis 1. Reinforcement learning, when it's specifically incentivized by compositional data, teaches a kind of structural generalization, not just input-output mapping for the examples it saw. It learns the how.
That's exactly what this first result suggests.
Okay, but that still leaves the crucial mechanism question unanswered. We see generalization when RL is trained on compositional data, level 2 problems. But does that generalization come from the data itself just seeing examples of FGX? Or does it specifically come from the optimization method, the reinforcement learning process with its sparse rewards?
This is where the head-to-head comparison in Figure 3 comes in. It directly pits the RFT level 2 model against the RL level 2 model. Remember, both were trained on the exact same set of level 2 compositional problems.
But RFT saw the perfect step-by-step reasoning trace for every single training example, while RL only got that binary pass-fail signal on the final answer. My intuition still says RFT should have the advantage here for learning structure.
That's what makes this result, takeaway 2, so fascinating and maybe counterintuitive. The RFT level 2 model performs, well, frankly, abysmally. Despite seeing the Oracle's perfect intermediate steps for all level 2 training problems, it fails badly at generalizing. Even on held-out level 2 problems, same difficulty it trained on, it only scores about 15% accuracy.
Only 15% on the same level? That's really low for a supervised method that saw perfect examples.
It's surprisingly low. And its generalization to unseen level 3 problems is even worse, barely getting above 2.6%, essentially noise level again. Seeing the steps didn't help it learn the general rule.
Wow. Okay, now contrast that with the RL level 2 model. Same training data, level 2 problems, but only the binary reward.
The RL level 2 model achieves 64% accuracy on the held-out level 2 test problems. And maybe more importantly, it achieves 27% accuracy on the unseen level 3 problems.
Okay, let's break that down. On level 2, RL beats RFT 64% to 15%. That's more than a 4-fold difference. And on level 3 generalization, it's 27% versus less than 3%. That's nearly a 10-fold difference. This seems to blow my intuition out of the water. How can RL, with less information, just pass-fail, learn the structure so much better than RFT, which saw the perfect structure explicitly?
This is where we get into the weeds of how these methods optimize. RFT, because it uses next token prediction, NTP, is fundamentally a supervised method aiming for local fidelity, meaning it tries to make the model output the very next token that matches the Oracle's reasoning trace at each step. Its objective is optimized locally, token by token. If the model makes a small mistake early on, NTP tries to correct that specific local token choice, but it doesn't necessarily enforce or discover the robust, abstract strategy or plan that leads to the correct final answer across many different problems. It's focused on mimicry.
Okay, local mimicry. How is RL different?
RL, especially policy gradient methods like the GRPO used here, operates differently. It's performing a kind of global search over the space of possible reasoning strategies or policies. Its sole objective is to maximize the probability of generating the final correct output, achieving that binary reward. To consistently get that reward across many different level 2 compositions, the model is pressured to discover the most robust and generalizable strategy. It needs to find the underlying pattern, the abstract systematic structure of function chaining, because that's the only reliable way to succeed across the board.
So RL's focus on the final outcome forces it to learn the general procedure, while RFT's focus on intermediate steps might paradoxically make it overfit to the specific traces it saw.
That seems to be the implication here. The search for a robust strategy, driven by optimizing the final outcome, proves to be the crucial ingredient for learning generalizable compositional skills. And that's something that just mimicking the intermediate steps with NTP seems to fail to capture effectively in this setup. Compositional data is necessary, but apparently not sufficient. You need the RL optimization on top.
Okay, this is compelling. We've established within this synthetic string world that RL seems uniquely capable of teaching genuine, generalizable compositionality. But the really big question, the ultimate test of whether this is a deep cognitive skill, is transferability. Is this compositional ability just a neat trick the model learned from manipulating strings like Func16 and Func2, or is it something more fundamental? Is it an abstract, transferable meta skill that could potentially apply across completely different domains?
That's exactly the question they tackled next. Does learning to compose string functions help the model compose, say, mathematical functions? #tag 4.1, the cross-task experiment setup, table 1. To test this, they introduced a completely separate, unrelated task domain, the countdown task.
Like the old game show. Given a target number and a set of starting numbers.
Precisely. The model is given, say, 6 integers and a target number, and its task is to construct a mathematical expression using standard arithmetic operations: addition, subtraction, multiplication, division that combines the input integers to exactly hit the target number.
Okay, so in this domain, the atomic skills are the basic arithmetic operations themselves, knowing how to add, subtract, multiply, divide.
Right. And compositionality here means correctly chaining those arithmetic operations together in the right sequence, respecting order of operations perhaps, to solve the puzzle and reach the target. A level 3 or level 4 countdown problem might require multiple steps of calculation.
So completely different domain, different atomic skills. How did they set up the transfer experiment?
Well, first, there's an obvious prerequisite. The model can't show compositional skill in math if it doesn't know basic math, right? So they had to make sure the models being tested had first acquired the atomic skills for the target task. They did this using RFT in stage 1 again, but this time on basic countdown problems, like single operations. So some models learned atomic string skills, some learned atomic countdown skills, and some learned both.
Okay, prerequisites established. Then the key comparison comes from how they handle stage 2 compositional training and testing.
Exactly. We need to look carefully at the comparisons shown in Table 1 and Figure 4. Let's focus on 3 critical groups. 1. Multibase, the baseline. This model has the atomic skills for both domains. It learned the string functions via RFT and the countdown arithmetic via RFT in stage 1. But crucially, it received no compositional RL training in stage 2 on either task. It knows the pieces, but hasn't been trained to compose them using RL.
Our baseline for non-compositionally trained performance?
2. String base, plus RL L1 plus 2, the control. This model learned atomic string skills in stage 1, and then got the successful compositional RL training, level 1 plus 2 mix, only on the string task in stage 2. But critically, it lacks the atomic countdown arithmetic skills.
So we expect this one to fail completely on the countdown task, right? To prove you need the domain-specific atomic knowledge.
Precisely. It's a sanity check. Knowing how to compose strings shouldn't magically teach you multiplication if you never learned it. 3. Multibase plus RL L1 plus 2, the transfer test. This is the key group. Like the baseline, it has both sets of atomic skills, string RFT and countdown RFT from stage 1. Then, just like the control group, it received compositional RL training, level 1 plus 2, in stage 2, but only on the string task.
Yeah.
It never saw RL applied to countdown problems.
Okay, so this model knows basic arithmetic from stage 1 RFT, and it learned the skill of composition from doing string problems with RL in stage 2. The question is, does that composition skill learned purely on strings help it perform better on the countdown task compared to the baseline that only knows atomic math?
That's the million-dollar transfer question. If this group significantly outperforms the multibase baseline on countdown, it's strong evidence that the compositional skill learned via RL is abstract and transferable. #tag 4.2 transfer results on countdown. figure 4 analysis.
So what did figure 4 show? Did the controls work as expected?
Perfectly. Observation 1 is that the control group, string base plus RL L1 plus 2, the one that knew how to compose strings but didn't know atomic math, failed completely on the countdown task. Its accuracy was near 0.
Okay, good. That confirms the prerequisite. You absolutely need the task-specific atomic knowledge. Composition skill alone isn't enough.
Right. But now for the exciting part. Observation 2, the transfer success. This is takeaway 3. We compare the multi-base baseline, atomic math, no compositional RL, against the transfer test group, multi-base plus RL L1 plus 2, atomic math plus string compositional RL.
How did they stack up on the countdown problems?
Significantly different. Let's look at performance on level 3 countdown problems. These require a few steps of arithmetic chaining. The multi-base baseline, just knowing the atomic operations, achieves somewhere around 17% accuracy.
Okay, 17% baseline.
Now look at the transfer test group. This model, remember, learned compositionality only by chaining Func 16 and Func 2 unlike on abstract strings using RL. When tested on level 3 countdown, it achieved 35% accuracy.
Wow, from 17% to 35%. That's double. An 18 percentage point improvement on a math puzzle task driven entirely by RL training on a completely unrelated string manipulation task.
It's a genuinely astonishing result, I think. It strongly suggests the compositional skill isn't tied to the specifics of strings.
Does that advantage hold up on even harder countdown problems like level 4?
It does. While the absolute accuracy drops for both models as the problems get harder, level 4 countdown is tough, the RL train transfer model consistently maintained a significant advantage over the baseline. It reached about 6% accuracy on level 4 countdown, whereas the baseline models were essentially at 0 performance.
This is really quite profound. How can optimizing string manipulation possibly teach the model how to better chain arithmetic operations for a math puzzle? What's the underlying mechanism?
It strongly implies that the RL training process, driven by the need to succeed on compositional string tasks, optimized something deeper than just the execution of Func 16 or Func 2. It seems to have optimized the meta skill of abstract planning and sequential execution. The model learned, through the pressure of the reward function and the structure of the compositional string data, a general cognitive routine. When I encounter nested dependencies, regardless of the domain, the correct procedure is to resolve the innermost operation first, then use that output as the input for the next operation layer and repeat this systematically until the final result is obtained.
So it's like learning an algorithm for structured decomposition and execution.
Exactly. It appeared to be a structural planning mechanism, a way of thinking that isn't inherently tied to strings or arithmetic, but applies to any task with that kind of nested sequential structure. And this finding offers a really compelling potential explanation for why RL fine-tuning often seems to provide generalized reasoning improvements in other contexts, like in papers on logic RL or the guru model you sometimes see. It might be that those improvements are fundamentally driven by RL enhancing this core, transferable ability to sequence already known steps more effectively, applying it across different domains. #tag 5, challenging the re-ranking illusion.
Okay, we've seen RL drives generalization. It beats RFT even with less supervision. And the skill it teaches seems to be a transferable meta skill. This brings us back to that initial skepticism, the re-ranking illusion. The core critique, as we said, is that RL doesn't really teach anything new. It just gets better at finding the good answers that the base model could have generated anyway, maybe if you just sampled from it enough times.
Right. The argument is that the base model, pre-RL, already has the latent capability. Maybe it generates the correct answer 1% of the time and 99% junk. RL just learns to amplify that 1% and suppress the 99%. So the performance gain looks impressive, but it's selection, not creation.
And the typical evidence cited for this is the pass-at-hair metric. The idea is that if you let the base model generate t-taller different answers, where tallers is large, like 100 or 1,000, its probability of getting the right answer at least once, pass at k, should eventually catch up to the RL model's pass-at-1 performance if RL is just re-ranking. The gap should shrink as tau increases.
Precisely. So the researchers put this directly to the test using a pass-at-k analysis, but crucially, they analyzed it across different levels of difficulty. This is shown in Figure 5, and it provides a much more nuanced picture. #tag 5.1 pass-at-k analysis across difficulty. Figure 5 analysis. The key insight here is that you have to segment the analysis by how hard the problems are for the base model. Let's start with easy problems. That's level 1 and level 2 compositions in this study. On these problems, the RFT base model, the one that learned atomic skills but had no compositional RL, actually does have a reasonably high potential to solve them if you sample enough. Its pass-at-k score climbs significantly as tau R increases.
Okay. And what happens to the performance gap between this RFT base at high ogles and the RL level 1+2 model at pass at 1?
On these easy problems, the gap does shrink considerably as tidal increases for the base model. The RL model is still better at pass at 1, but the base model can eventually find the solution often enough if you give it many tries.
So on problems the base model already has a decent latent ability to solve, the results are actually consistent with the pessimistic re-ranking narrative. RL is acting like a more efficient sampler.
Exactly. This shows the critics aren't entirely wrong. Re-ranking is likely a significant part of what RL does when the underlying task isn't fundamentally challenging the base model's capabilities.
But what happens when the problem gets genuinely hard? When it demands a skill the base model really seems to lack.
Now we look at the hard problems levels 3 through 6 in this study. These are the deeper compositions where the base model's accuracy, even at high dollars, remains very low. It genuinely struggles to generate the correct compositional reasoning. And here, the trend reverses dramatically. On these hard problems, the performance gap between the RL level 1+2 model at pass at 1 or even pass at K and the RFT-based model at pass at K widens substantially as the killer grows.
Wait, the gap gets bigger as you give the base model more chances? How does that work?
Let's take level 5 as the prime example they highlight. At pass at 1, giving each model just one shot, the performance gap between the RL model and the RFT base is noticeable, but maybe not huge, around 4 percentage points. But now let's increase Tockler for both. Let's allow each model to generate, say, 124 different attempts pass at 124. The RO model's pass at 124 score shoots up significantly, as expected, but the RFT-based model's pass at 124 score barely budges from its near-zero pass at 1 score. As a result, the performance gap between them at pass and 124 explodes to approximately 25 percentage points.
That's incredible. If RL were only re-ranking solutions that the base model could already generate, then giving the base model 124 tries should have allowed it to find those solutions eventually, closing the gap.
Exactly. The fact that the gap widens so dramatically proves that the RL-trained model is capable of generating correct reasoning trajectories and final solutions for these hard compositional problems that the base model simply cannot generate, or can only generate with vanishingly small probability, even when given massive sampling budgets.
This feels like definitive evidence against the universal claim of the re-ranking illusion. It suggests RL is genuinely expanding the model's capabilities, teaching it to reach solutions that were previously unreachable.
That's the conclusion the study draws, and it's takeaway 4. The pessimistic re-ranking view seems to be, at least partly, an artifact created by evaluating or training RL primarily on tasks that are insufficiently challenging tasks, where the base model already possesses a high pass at K potential. When you introduce tasks that require genuinely new, complex skills, like deep compositionality here, where the base model's pass at K is low, RL demonstrably pushes the performance limits far beyond what re-ranking alone could achieve. It seems to be true skill acquisition in these harder regimes.
Okay, the quantitative pass at K analysis is powerful. But beyond just getting the right answer more often, we need to know if the model's internal approach to solving the problem has actually changed. Did RL teach the model how to think compositionally in a different way?
This is where the qualitative analysis comes in, looking at the types of mistakes the models make when they fail. Figure 6 analyzes the failure modes specifically on level 3 problems, which are hard enough to show differences, but not so hard that everyone gets 0.
How did they categorize the failures? What kinds of mistakes can the model make on a compositional problem like FGKX?
They focused on failures related to understanding the compositional structure. They defined 3 key categories. 1. Ignores composition. This is the most fundamental failure. The model completely fails to recognize or attempt the nesting structure. For example, it might just apply the outermost function directly to the initial input, $6, ignoring text entirely.
Okay, total failure to see the structure.
2. Incorrect composition. Here, the model tries to handle the nesting but gets it wrong. It might misinterpret the order of functions, VNAM, compute VACI G instead, or miss a level or incorrectly pass intermediate results. It acknowledges structure but executes it incorrectly.
Still a high-level structural error.
3. Atomic error. This is a more subtle failure. The model correctly parses the entire compositional structure, e.g. it knows it needs to compute KKX and then takes says no case. It follows the right plan, but simply makes a mistake in executing one of the individual basic atomic steps, like vis calculating func 2 or func 16.
So the plan was right, but the execution of a basic step was flawed. This implies the compositional skill itself was present.
Exactly. The type of error tells you where the model's reasoning broke down. So what were the failure profiles for the baseline models, the RFT1 and the RL level 1 atomic only?
What did their pie charts of errors look like?
Their failures were overwhelmingly dominated by the high-level structural problems. For both the RFT level 2 baseline and the RL level 1 model, the ignores composition category accounted for more than 50% of their errors on level 3 problems.
Over half the time, they didn't even try to follow the full nested structure.
Right. And the incorrect composition category accounted for most of the rest, maybe another 35% or more. They fundamentally lacked the ability to reliably parse and execute the compositional plan. Atomic errors were relatively rare for them because they usually failed before even getting to the final atomic step.
Okay, that's a clear picture of structural failure. Now, what about the model that was successfully trained with RL on compositional data, the RL level 2 model?
This is the fifth key takeaway, the behavioral transformation. When you look at the failure modes of the RL level 2 model, the picture changes dramatically. First, it completely eliminates the ignores composition error category. Right. That failure mode drops to 0%. The RL training has successfully taught the model the imperative. You must execute functions sequentially according to the nesting.
Wow, 0% ignores composition. That alone is huge. What happens to the other categories?
The incorrect composition errors also decrease significantly, though not quite to 0. But the most striking shift is that the model's primary failure mode becomes atomic error. Making a mistake in executing one of the basic level 1 functions now accounts for about 55% of its mistakes.
That is a profound cognitive shift. It means that when the RL level 2 model fails, it's most often failing after having correctly understood and planned out the entire complex compositional structure. Its vulnerability has shifted from misunderstanding the high-level plan to making minor slips in the low-level execution steps.
Precisely. RL didn't just make the model slightly more accurate overall, it fundamentally rewired how the model approaches compositional problems. It taught the model to correctly parse and execute the compositional plan, transforming its failure profile from one dominated by architectural misunderstanding to one dominated by occasional execution errors within a correct structure. #tag 6, detailed example of behavioral shift.
Okay, this abstract idea of a behavioral shift is compelling, but it would be great to make it concrete. Let's walk through a specific level 3 composition problem, maybe the one they use in Appendix F.2 of the paper, where we can actually see the difference in the reasoning traces produced by the failing RFT model versus the successful RL level 2 model. #tag 6.1, the level 3 composition problem.
Good idea. Let's use that example.
Yeah.
The problem involves predicting the output of a main solution function applied to the input string hkok. And buried inside main solution is a 3-level composition. Korana is FGTOS, which corresponds to the specific function chain func10, func42, func2x.
Okay, input 6 doctor in 3 nested functions, func2go, then func14, then func10. We need to know what these functions do.
Right. Let's reestablish their definitions from the paper's context for this example. The innermost function, kx is func2ust. This one removes vowels, a, e, i, o, u. The middle function, prex, is func2tel. This one duplicates every character in its input string. The outermost function, func10, this one applies alternating case to its input string. Index 0 lower, index 1 upper, index 2 lower, etc.
Okay. Remove vowels, then duplicate characters, then alternate case, applied to utek. So for the correct solution, the successful RL level 2 model needs to execute this chain systematically from the inside out. Let's trace that correct path first. We start with sextackles equals hextalk.
Step 1, innermost function, func2. Apply remove vowels to hec. The vowels are O and E. Removing them leaves us with the intermediate result, htk.
Got it. Okay.
Step 2, middle function, func14. Apply duplicate every character to that intermediate result, htk. Duplicating h and k yields the next intermediate result.
Okay, step 2.
Step 3, outermost function, func10. Apply alternate case to hgtk. Index 0h is lower, 1h is upper, 2t is lower, 3t is upper, 4k is lower, 5k is upper. This gives the final correct output, hhttkk.
hhkk. Okay, that's the target. That 3-step chain, requiring recall and application of 3 different functions in the right order with intermediate results passed correctly, is the rigorous logic the model needs to discover and apply. #tag 6.2, step-by-step comparison of reasoning.
Right. Now let's contrast that correct trace with how the paper shows the failing models attempting this problem, starting with the RFT baseline, the one that saw supervised examples but still failed.
Okay, looking at the example trace for the RFT model, specifically the RFT level 2 model from figure 6, which saw level 2 compositions, it exhibits a classic ignores composition failure, even on this level 3 task. The trace shows the model latching onto one of the functions mentioned, func10, alternate case, but applying it directly to the original input, atcheck. It seems to completely ignore the existence and the required prior execution of the inner functions, func14 duplicate and func2. Remove vowels. So it just does func10 check.
Essentially, yes, or something similarly broken where it doesn't respect the full nesting. The trace might show it thinking about func10 and outputting something like htech based on applying that logic alone to the original input. It fails to execute the necessary sequence, then jek htech.
A complete failure to parse and execute the required three-step structure, even though it was trained with supervised examples of two-step structures. The supervision didn't instill the general principle.
It seems not. The focus on local token mimicry in RFT didn't force it to learn the abstract structural plan.
Okay, what about the RL Level 1 model? This one mastered atomic skills with RL, but never saw RL applied to compositions. How does it fail on this Level 3 problem?
The RL Level 1 model, according to the failure analysis and example type, typically shows an incorrect composition failure. It actually attempts to compose, which is arguably a step up from the RFT model that ignored composition. It seems to recognize there's nesting involved.
But it gets the structure wrong.
Exactly. The example trace might show it correctly applying the innermost function, func2, remove vowels, to htake to get htk. That's a good first step. But then it messes up the sequence. It might completely skip the middle step, func14, duplicate, and incorrectly apply the outermost function, func10, alternate case, directly to htk.
Ah, so it computes func10, func2 instead of the full func10, func10.
Precisely. It calculates func10 htk, which would yield htk. It has misinterpreted the nesting depth or the specific functions involved at each level. It had the atomic skills. It calculated func2 correctly. But its sequencing logic, its understanding of the compositional plan, is flawed.
Still a high-level structural failure, just a different flavor than ignoring it completely.
Right. Now, contrast both of those failures with the trace from the successful RL Level 2 model.
The one trained with RL on Level 2 compositions.
Yes. Its reasoning trace for this Level 3 problem looks entirely different. It shows a flawless execution of the compositional plan. The trace explicitly documents and executes the systematic sequence. 1. It correctly identifies the need to first compute func2 htech and correctly derives the result, htk. It correctly identifies that this result, htk, must then be fed into func14. It computes func14 htk duplicate characters and correctly derives htk. 3. It correctly identifies that htk must then be fed into func10. It computes func10 htkkk, alternate case, and correctly derives the final answer, httkk.
It follows the exact three-step logical chain we outlined earlier.
Perfectly. The key difference is that the RL optimization process, driven by the need to succeed on Level 2 tasks using only binary rewards, forced the model to acquire the abstract ability to parse and resolve these nested dependencies correctly. It learned the general procedure.
And even if this RL Level 2 model had made a mistake, say, in the final alternate casing step, an atomic error, the fact that its trace showed the correct structure and intermediate results would still place it in a fundamentally different category than the other models.
Absolutely. Its failure would be an execution slip within a correct plan, not a failure of the plan itself. This acquisition of the ability to construct and follow the correct compositional plan is what fundamentally separates the successful RL model from those relying solely on supervised learning traces or atomic RL training in this study. It genuinely learned how to compose. #tag outro.
So, wrapping this all up, this deep dive into compositional skill acquisition seems to provide a remarkably clear answer to that huge opening debate in AI. Reinforcement learning, when it's properly set up and incentivized with the right kind of complex compositional data, appears to be far more than just a high-powered editor or re-ranker.
Yet, the evidence strongly suggests it's a true skill acquisition mechanism. It seems capable of teaching LLMs genuinely new, cognitive skills that are demonstrably generalizable to harder problems, transferable across domains, and which fundamentally change the model's underlying reasoning behavior.
We saw that through multiple lines of evidence. Takeaway 1, the massive generalization leap, where training on Level 2 problems unlocked significant performance on unseen levels 3 through 6.
Takeaway 3, the demonstration that this compositional skill acted like a transferable meta-skill, boosting performance substantially in the completely unrelated countdown math task.
Takeaway 4, the pass at K analysis, showing that on genuinely hard problems, RL expands the model's performance limits far beyond the base model's reach, directly contradicting the simple re-ranking narrative in that regime.
And maybe the most telling, takeaway 5, the qualitative behavioral shift, where RL training eliminated the ignores composition failures and shifted the primary error mode to atomic errors, showing the model learned the plan even if it sometimes fumbled the execution.
These findings seem to deliver a pretty clear mandate for how we should think about developing more capable LLMs, don't they?
I think so. It suggests a two-pronged approach might be optimal. First, you need continued focus on base model development, ensuring the models have broad and robust foundational knowledge, those atomic skills, probably acquired through methods like large-scale pre-training and perhaps RFT on basic tasks. But critically, if we want LLMs capable of true multi-step reasoning, reliable complex tool use, or tackling problems with deep logical structure, we likely need to follow that up with targeted post-training strategies, and specifically reinforcement learning, using reward signals and data that heavily incentivize and reward generalized compositional execution.
So it's less about just making the model nicer or safer with RL and more about using RL to actively build higher order cognitive abilities on top of the base knowledge.
That seems to be the potential. The debate, based on this evidence, maybe shifts entirely now. It's perhaps no longer Keane's. Can RL teach new skills? The answer here seems to be a qualified yes. The more interesting question becomes, how should we design RL tasks, data, and reward landscapes to incentivize the maximum amount of generalizable skill composition?
Right. If this kind of function chaining, this compositionality, is a key mechanism for generalizing from easy problems to much harder ones, what's the next layer of abstract structural complexity we need LLMs to master? Is it maybe learning conditional branching, if X do Y else do Z, in a general way? Or perhaps recursive execution? And crucially, how do we engineer the training environment, the rewards, to specifically encourage the emergence of that kind of abstract transferable learning?
That really does feel like the exciting frontier. What are the fundamental building blocks of complex reasoning, and how can we use RL to get models to learn them, not just for one task, but as general cognitive tools?
A fascinating question to ponder. That's all we have time for on this deep dive.
Welcome back to the deep dive. We are jumping straight into one of the most consequential, really high-stakes debates shaping the direction of artificial intelligence right now. It's this question: does reinforcement learning, RL, the technique we use after pre-training, does it actually give large language models new cognitive skills?
Or is it just polishing them?
Exactly. Or is it just amplifying capabilities that were kind of already baked in during that massive pre-training phase?
It's this fundamental tension, isn't it, between, let's say, genuine creation and just refined optimization.
Right.
And historically, RL has delivered foundational learning. I mean, you think about AlphaGo, AlphaZero. These systems learned incredibly complex general skills almost from scratch, from a blank slate.
Yeah, completely new strategies emerged there.
But when you apply RL to LLMs, these models that already have, trillions of tokens of knowledge, well, that's led some people to take a more pessimistic view. There's some really influential recent work, Wu et al., for example, suggesting RL mostly just re-ranks existing reasoning strategies.
Re-rank, so it makes the model better at finding a path it already kind of knew.
Exactly. Better at finding a correct path rather than inventing a truly novel way to solve the problem.
That distinction, better editing versus actual invention, it's everything, isn't it?
It really is.
Because if RL is only a fantastic editor, then relying on it for, say, AGI capabilities or even just deep generalization, maybe that's misplaced. We might just hit a ceiling, defined by whatever was in the pre-training data.
And that's precisely why this study we're diving into today is so critical. Our mission really is to rigorously explore a research framework they designed specifically to cut through that noise, that potential contamination.
Okay.
They want to scientifically test what they call the RL compositionality hypothesis.
Compositionality hypothesis.
Okay. Yeah, and the framework is synthetic, it's controlled, and it's directly inspired by cognitive science, actually. Specifically, Anderson's work back in '82 on how humans learn new skills by combining existing, simpler skills.
So we're basically setting up a kind of pristine cognitive lab, but for LLMs.
That's a great way to put it.
And the core concept, you mentioned 5X and JICS, it sounds simple, but it feels like it has huge implications.
It does. The idea is, if an LLM has definitely mastered two basic skills, let's call them 5X and LX, can RL then teach it to systematically execute a totally new, unseen compositional skill? Let's call that JEXer, where XX is just replied to the result of JEX. So at ARX addresses JEXXX, right?
Like nesting functions, building a chain.
Exactly. It's about building that robust chain of capabilities. If we can isolate this mechanism and really prove that RL teaches the systematic and generalizable composition of Yeltsin dollars, especially across new difficulty levels,
Then we've got concrete evidence.
then we have solid evidence for genuine structural skill acquisition, not just re-ranking. So let's start by defining the tools they used, the framework itself.
Okay, so the first big hurdle, maybe the biggest, was this data contamination issue you mentioned.
Absolutely critical.
With these massive models like Llama, you just never know for sure if they've seen similar problems or the logic behind them somewhere in that vast training data. So they needed this clean test bed. And they focused on deductive reasoning, but applied to string transformations. Why strings?
Well, using string transformations is actually quite brilliant here. It's complex enough that it requires genuine step-by-step reasoning. You can't just guess.
Okay.
But it's also structured enough that you can formalize it mathematically, you can control it very precisely, and the foundation of this whole experiment rests on being absolutely rigorous in defining what counts as a skill.
Right. We need definitions.
So, formally speaking, a skill here is defined as the ability to reliably infer the output of one of these specific string transformation functions. Let's call it again. Given some input string 6 balls.
And how many of these functions were there?
They curated a set of 25 unique functions. These covered a range of operations, things like manipulating characters, filtering them out, reordering them, changing the structure.
So 25 basic building blocks.
Exactly. These 25 functions are the sort of basic cognitive building blocks the model needs to learn first.
And these blocks aren't all the same difficulty, right? They're categorized.
Yes, and this is crucial. They're categorized by complexity, specifically by the depth of composition.
Okay, so what are the categories?
2 key types, defined by depth. First, you have atomic skills. These are level 1. They represent a single, non-decomposable transformation, like just applying Func 16x. Mastering these is the baseline, the foundation.
Just one step.
One step. Then second, you have compositional skills. These are level 2 or higher. They involve nesting these functions, combining them, like applying Fate GX, that would be level 2.
And FGKX would be level 3 and so on.
Precisely. The key variable they control is this difficulty level, and it maps directly onto the nesting depth. Level dollar means you're chaining model functions together.
That's really important. It means if a model aces level 1 but fails at level 4, we know the struggle is purely about the complexity of chaining 4 steps, not some hidden variable.
Right. It isolates the compositional challenge itself. #TagTech1 button defining atomic and compositional skills.
So just to really nail down that notation,
Huh.
level 1 is 1.3 and level 3 is FunGX.
Exactly. And this structured complexity becomes absolutely vital later when we test for generalization. You know, the big question. Can a model that was only trained on level 2 problems suddenly figure out how to solve a level 3 chain it's never seen before?
But that contamination risk still looms, doesn't it? If they name these functions descriptively, like reverse string or remove vowels.
Oh, absolutely. If they'd done that, the LLM, with its vast pre-training, might just retrieve a definition it already knows, or maybe even find Python code for it somewhere.
And that would completely bypass the reasoning we want to test. It becomes lookup, not deduction.
Precisely. And that leads us straight to their decontamination strategy. It's quite an elegant solution, actually, to this pervasive problem in LLM research.
How did they solve it?
To guarantee, absolutely guarantee, that any skill the model shows is genuinely learned from their training protocol, they assigned totally meaningless identifiers to every single function.
Right.
Func 16, Func 7, Func 2, and so on. Just arbitrary numbers. There's no clue in the name about what the function actually does.
So the model has to learn the behavior.
It has to learn the behavior by observing input-output examples, or later, the reasoning trace during stage 1 training. The task becomes unsolvable without internalizing what Func 16 actually means algorithmically.
So it's forced deduction, no shortcuts.
Exactly. No memorized lookup based on the name. This means we can be much more confident that any ability we see, especially the compositional ability later on, is a skill acquired during this specific experiment, not just some latent ability woken up by a clever prompt.
Okay, that feels really robust. That makes the findings potentially very powerful. #tag 1.2 example of an atomic skill derivation, Func 16. Right, let's make this really concrete then. Before we even get to putting functions together, let's see what's involved in just one basic level 1 atomic skill. You mentioned Func 16. What does it do?
Okay, Func 16 is defined like this. It removes adjacent duplicate characters from a string S.
Removes adjacent duplicates. Okay, so if you had hello, the L's are adjacent, so one gets removed, giving hello.
Exactly. And if you had bookkeeper, you'd get booper. The U becomes U, K becomes K, E becomes E.
Got it. So let's use their example input string, do_s, equals tafis. How does the model need to reason step by step to get the right output for func16?
Okay, this is where we need to appreciate the rigor. The model isn't just spitting out the final string. In stage 1, it's learning the explicit algorithmic trace. It's like how you or I might internalize a set of rules.
Like showing your work in math.
Exactly like showing your work. So we start with the input style, onkils tasias. The internalized algorithm for func16 would proceed something like this. First, input condition check, a base case. Is the input string empty?
No, tayits is not empty.
Right. If it were empty, the function would just return an empty string. Since it's not, we proceed. Second, initialization. We need to start building our result. The algorithm always initializes a result list with the very first character of the input string $.
Okay, so $C is T. Our result starts as just TC.
Correct. Now, third, the iterative loop. We iterate through the rest of the string, starting from the second character, $C on. For each character, let's call it $2, we compare it against the last character currently in our result list, which we can call result 1.
So it's always a local comparison. Just look at the current character and the very last one added to the result.
Precisely. It doesn't need to remember the whole history, just the last character successfully added. That's the core logic. The conditional check is if cschess result-1.result.append. If the current character is different from the last one added, we append it.
Okay, let's trace that for tikis. Our result is T. The next character is I.
Right, so tikis equals I. Is I different from the last result character, T?
Yes.
So append I, result is now a T.
X character is H, different from I.
Yes. Append H, result T, high H.
Next is E, different from H.
Yes. Append H, result T-I-H.
Next, A, different from E.
Yes, append A, result T-I-H-A.
Okay, now we get to the interesting part. Next character is S, different from S.
Yes.
Append S, result T-I-H-E-S.
And now the last character of the input is also S. Is this S different from the last character in our result, which is also S?
No, they are the same. Take ES result 1 excel S, so the condition here result 1 is false.
So the algorithm skips the append step here. It doesn't add the second S.
Exactly. That's how the adjacent duplicate gets removed. The loop finishes.
So the model's trace has shown it did, 6 comparisons and made one crucial decision not to append. Precisely. And the final step, step 4, is just output conversion. We join the characters in the final result list. TAE is back into a string.
Giving taihees.
Giving taihees, and that entire sequence, understanding the input, initializing, the iterative local comparisons, the conditional append, and the final output generation that is the atomic skill for func16. This is the foundation the LLM has to master in stage 1. Without this level of detailed execution, none of the composition stuff can even begin. #2, the 2-stage training protocol.
Okay, so that establishes the basic skill. Now, how did they actually train the model? You mentioned 2 stages.
Yes, of a very carefully designed 2-stage protocol. This was crucial to cleanly isolate the specific effect of reinforcement learning on learning compositionality. And they used Llama 3.18b Instruct as the base model, which, already has a huge amount of knowledge.
Right, starting with a capable model. So stage 1, this is purely about getting those 25 atomic skills down pat, right? Ensuring the model can reliably execute func16, func2, all of them.
Exactly. Stage 1 is the prerequisite training. And they used a specific method here called rejection fine-tuning, or RFT.
RFT, can you define that quickly? Why RFT?
Sure. RFT, rejection fine-tuning, comes from Dong et al. In 2023. It's essentially a high-quality form of supervised learning. The key reason they chose it is that it trains the model only on the correct reasoning trajectories.
The step-by-step show your work traces we just went through.
Precisely. The model learns by imitating perfect examples of the correct logic for each atomic function. It sees the input, the detailed steps, and the final output.
And this is where it sees the actual code.
Yes, a really critical detail. Stage 1 is the only time the models ever see the explicit Python function implementations, like the def func16's code.
Oh, okay.
They are shown the code definition alongside the correct execution trace for specific examples. This is designed to make sure the model truly internalizes the underlying algorithm for each of the 25 atomic skills.
Makes sense. They need that ground truth. And how did they generate the training data for this stage?
They were smart about efficiency. They generated about 50,000 level 1 problems, just single function applications. But then they tested the base Llama model on these problems before any stage 1 training.
Why?
to filter out the easy stuff. Any problem where the initial off-the-shelf llama model already got 100% accuracy, they just discarded it.
Focus the training on where the model actually needs to learn something new.
Exactly. Focus on the non-trivial examples. This filtering resulted in about 116,000 high-quality training instances for Stage 1 RFT. So after Stage 1 is done, all the models used in the rest of the experiment have this robust foundation of the 25 atomic skills.
Okay, foundation laid. Everyone knows the basics. Now for the main event, Stage 2, this is where composition comes in.
Yeah.
And the conditions change significantly, right?
Fundamentally, the biggest change, the explicit function definitions, the Python code, gone, hidden. The model now only sees problems presented as compositions. Like, it will see the instruction to compute func2, func16x, for some input x. It knows what func2 does and knows what func16 does from Stage 1, but it has never seen the code for them together, and it has to figure out how to chain them.
And this is where the comparison happens, RL versus the RFT baseline.
Yes. This is the core experimental comparison. They take models that have completed Stage 1 and train them further using the exact same set of compositional problems, Level 2 problems mostly, but using two different training mechanisms. This lets them separate the effect of seeing compositional data from the effect of the optimization algorithm itself.
Okay, let's break down the two groups. Group 1.
Group 1 is the offline RFT baseline. Think of this as continued supervised learning. It still uses RFT based on next token prediction, NTP. It's shown correct step-by-step reasoning trajectories for solving compositional problems like them two tags.
So it sees perfect examples of how to do the composition, the step-by-step, imitation learning again.
Exactly. This group tests the hypothesis, is just seeing how to correctly compose functions enough to learn the general skill. Can the model generalize just by imitating?
Okay. And Group 2, the RL group.
Group 2 uses online RL. Specifically, they used a method called Group Relative Preference Optimization, or GRPO. But the crucial difference is the feedback signal. This RL model does not see correct reasoning traces.
No step-by-step guides.
None. It only gets binary rewards. It generates its own reasoning trace and a final answer. If the final answer is correct, boom, reward of 1.0. If the final answer is wrong, reward of 0.0. That's it.
Wow, okay, that's a huge difference. Just pass-fail on the final output.
It is. The RFT baseline model is shown the blueprint and told, copy this. The RL model is essentially told, here's the input, here's the target output structure, like a free X dollar. Figure out a reliable process to get the right final answer. It has to explore and optimize its internal strategy to maximize that simple win-loss reward.
So the RL model is forced to learn the how more deeply, because it's not just copying the what.
That's the hypothesis. It forces the model to internally organize and chain the atomic skills it learned in Stage 1 into a reliable, systematic program for composition, because that's the only way to consistently get the reward.
And within RL, they tested slightly different setups for Stage 2.
Yes, they had a few configurations to probe generalization. One was RL Level 1. This model was only trained further on atomic Level 1 tasks using RL. It never saw compositional problems in Stage 2. This acts as a crucial control. Does just getting better at atomic skills via RL help with composition? Spoiler, not really.
Okay.
Then RL Level 2. This model was trained only on Level 2 composition problems using RL.
The core compositional training.
Right. And finally, RL Level 1 plus 2. This one was trained on a uniform mix of both Level 1 and Level 2 problems using RL in Stage 2.
Okay, to really hammer home what's being learned in Stage 2, let's revisit that composition example.
Yeah.
Y dollars, let's use the functions you mentioned.
Well,
$5 is func2, remove vowels, and the dollars is func16 dollars, compress adjacent repeats. And the input is still $6, is still $6.
okay, so the model comes into Stage 2 knowing perfectly well how to execute func2 on its own and how to execute func16 on its own. The challenge now is the nesting func2, func16 tices.
It has to learn the chaining rule.
Exactly. The core challenge is the rigorous, systematic execution of these nested dependencies. It's a hierarchical structure. $J is inside $5. The model has to learn to 1, correctly parse the structure, realize it needs to compute $1 first. 2, execute that innermost function. 3, hold that intermediate result in memory somehow. And 4, use that intermediate result as the input for the next function outwards, $5.
So step by step for func16.
Okay. Input 6 axles, cells, choices,
Oh, yeah.
parsing. The model identifies the structure. It needs to compute $, and then compute y, mz.
Okay.
Step 1, inner function. It applies func16. We already worked this out. Func16 removes adjacent duplicates. The evis at the end becomes s.
Right, so the intermediate result is TIACZ FZ AEX ASE.
Correct. Zavel A plus does GX equals tie his isle. Now, this intermediate result Taihez is critical. If the model messes this up, or forgets it, or passes the wrong thing to the next step.
The whole composition fails.
Exactly. So assuming it got Sayas to Taihez correctly. Step 2, outer function biosede. It now applies funct2 to this intermediate result Taihez. So funct2.
And funct2 removes vowels. The vowels in Taihez are I, ia.
Right. So removing IAA from Taihez leaves.
Step 3. Final output. The final string is IL7.
Okay. So the compositional skill learned in stage 2 isn't just getting thucks. It's the reliable, ordered execution. Parse structure, do inner dollars, get intermediates, pass to outer 5, get final dollars. That is precisely it. It's learning that systematic process. And the big question is, can RL instill this process robustly enough that the model can then apply it to things it's never seen, like level 3, level 4, and so on? That's where we look at the results. #3RL as the key to generalizable skill acquisition. Okay, so now I get to the core experimental results. Did this setup work? Does RL, when paired with these compositional problems, actually teach a generalizable skill? Or does the model just get better at the specific level 2 problems it saw during training?
This is where we look at figure 2 in the paper, right?
Yeah.
It seems to show a really stark contrast.
It really does. Let's start with that control model, RL level 1. Remember, this model got RL training in stage 2, but only on the basic atomic level 1 tasks. It never saw compositions like 5GX during stage 2.
How did it do?
Well, it got really good at the atomic tasks, as you'd expect, achieved around 90% accuracy on level 1 problems, but it hit a wall, a generalization cliff, when faced with composition.
It couldn't handle level 2.
Barely. Its accuracy on level 2 problems it had never seen was below 25%. And for harder compositions, level 3 through level 6, accuracy was consistently near 0.
Wow. So knowing the bricks really well doesn't mean you know how to build the wall.
Perfectly put. It mastered the atomic skills, but completely failed to learn the principle of how to combine them.
Okay, so that's the baseline. Now, what about the model that was trained on compositions? The RL level 2 model. Remember, it only saw 2 function chains, Fiji levels, during training.
This is where it gets exciting. This model shows a massive leap in its ability to generalize, to solve problems far more complex than anything in its stage 2 training data.
This is the first big takeaway then.
This is absolutely takeaway 1. Training on simple level 2 composition problems using RL teaches a generalized principle of compositional reasoning. It's not just memorizing level 2 answers.
How big was the leap? Let's look at level 3 performance, those problems the model never saw in training.
Okay, compare the RL level 1 model, which scored maybe 5% on level 3. The RL level 2 model jumps all the way up to approximately 30% accuracy on unseen level 3 problems.
30%. From basically 0. On a task 3 levels deep it never explicitly trained for. That feels like a qualitative shift.
It is. The model hasn't just gotten slightly better, it seems to have internalized the abstract meta rule. Evaluate inner function, pass result to next function, repeat.
And does this generalization continue to even harder levels, like level 4?
It does. Level 4 accuracy, which was negligible, maybe 1% for the level 1 control model, it jumps to around 15% for the RL level 2 model.
Okay.
So this really validates their primary hypothesis. RL, when it's incentivized by this kind of compositional structure, seems to instill a cognitive program, an algorithm for composition that's abstract enough to apply to deeper nesting levels. It's learning the algebra of function composition, not just specific examples.
All right, so takeaway 1 is clear. Compositional data plus RL leads to generalization. But was the RL necessary? What about the other group, the RFT baseline? Remember, the RFT level 2 model saw the exact same level 2 compositional problems, but it learned via imitation by seeing the perfect step-by-step reasoning traces. Did that work too?
This is a crucial comparison shown in Figure 3. If the critics who believe in the re-ranking illusion are right that the capability is already latent in the LLM and you just need good data to bring it out, then this RFT level 2 model should have performed well. It saw perfect examples of level 2 composition.
But it didn't.
It did not, and this is takeaway 2. Compositional data by itself, even perfect imitation data, is not enough. The optimization mechanism matters.
How badly did the RFT model do?
Significantly worse than the RL model. First, it didn't even generalize that well to held out level 2 problems of the same difficulty it was trained on. It only got about 15% accuracy there.
Wait, only 15% on level 2. The RL level 2 model got, what was it?
The RL level 2 model achieved 64% on held out level 2 problems.
Wow, okay. 15% of XUS, 64% on the same difficulty level as training. That's huge.
It is. And when you look at generalization to level 3, the RFT level 2 model was even worse. It barely scraped above 2.6% accuracy. Remember, the RL level 2 model hit 30% on level 3.
Okay, I need to pause here. This seems really important. The RFT model was explicitly shown the correct step-by-step process for GXD. Why didn't it learn the general principle? Isn't imitation supposed to be a powerful way to learn?
Imitation learning, like RFT or standard supervised fine-tuning, is very good at teaching a model to map specific input states or patterns to specific output actions. It learns to match the distribution of the training data,
Okay.
but it often struggles with robust generalization, especially when faced with inputs or structures slightly outside that training distribution, like a level 3 problem when it only saw level 2. It learned to reproduce the level 2 traces it saw, but didn't necessarily extract the underlying abstract rule in a way that could be applied more broadly.
So how does RL overcome this? Why does that binary reward work better?
The thinking is that the RL setup, particularly with methods like GRPO, DAPO, that use that simple outcome-based binary reward, forces the model into a different kind of learning. Exploratory optimization.
Exploratory optimization.
Yeah. To consistently get that 1.0 reward across lots of different level 2 problems, the model can't just memorize specific traces. It has to discover and internalize a strategy, an algorithm for composition that works reliably, that is robust to variations. It needs a systematic program that always leads to the correct final answer.
So it's searching for the general rule itself, because that's the best way to maximize rewards.
That seems to be the implication. RL optimizes the search for the most robust, generalizable composition algorithm. It's not just copying solutions, it's discovering the underlying structure needed to generate them.
Okay, that makes sense. Supervised learning shows you what the answer looks like. RL in this setup forces the model to learn how to build a generalized program to find the answer, even for harder cases.
Exactly. The optimization mechanism provided by RL, not just the compositional data, seems to be the crucial ingredient, the secret sauce, for unlocking this kind of generalization.
Okay, so RL helps learn generalizable composition within the string task. But the really fascinating question, for me at least, is whether this learned skill is just specific to strings, or if it's something more fundamental. Could it be a transferable meta skill?
That's the next level of testing generalization, isn't it? If the model has truly learned the abstract structural rule of composition inner first, then outer, it should ideally be able to apply that same rule even in a completely different problem domain.
And they tested this using the countdown task.
Yes, the countdown task. It's a classic mathematical puzzle. You're given a set of numbers and a target number, and you have to construct an arithmetic expression using the given numbers, addition, subtraction, multiplication, division, to hit that target.
Ah, so composing arithmetic operations instead of string functions. Fundamentally different domain.
Completely different domain. But notice the structural similarity. Solving a countdown problem often involves chaining operations, like A plus B times C to O. It requires that same kind of step-by-step intermediate result thinking. Hashtag tag 4.1, the cross-task experiment setup. Table 1.
So how did they set up this transfer experiment? Obviously, the model needs to know basic math first.
Absolutely. That's the prerequisite requirement. Before they could even test for transfer of the compositional skill, they had to make sure the models first acquired the necessary atomic skills for the target task, countdown. Meaning they used stage 1 RFT again, but this time to teach the models how to perform basic arithmetic operations correctly: addition, subtraction, multiplication, division on the numbers involved in countdown. But critically, this RFT stage did not teach them how to chain these operations together to solve multi-step countdown problems, just the basics.
Okay, so all models being compared for transfer first, no basic arithmetic. Now, what were the key comparison groups? Table 1 lays this out.
Right. There are 3 crucial groups to understand to isolate the transfer effect. 1, string base plus RLL1 plus 2. This is a control group. It has the compositional skill learned via RL on the string task from the previous experiments, but crucially, it lacks the atomic arithmetic skills for countdown. It never went through the countdown RFT stage 1.
So it knows how to compose, but doesn't know the building blocks for math. What's the expectation here?
Expect it to fail completely on countdown. This just confirms that you need the task-specific atomic knowledge. Composition skill alone isn't magic.
Okay, makes sense. Group 2.
Multi-base. This is the main baseline for transfer. This model got RFT stage 1 training for both tasks. It knows the atomic string functions, and it knows the atomic arithmetic operations for countdown. However, it received no compositional RL training on either task.
So this tests if you just know the atomic pieces for both domains, how well can you compose them in the new domain countdown just based on imitation learning of the basics.
Exactly. This is the baseline compositional ability derived purely from RFT on atomic skills.
And the key group? Group 3.
3. Multi-base plus RL L1 plus 2. This is the critical transfer test group. Like the multi-base model, it has the atomic skills for both strings and countdown via RFT stage 1, but it also received the compositional RL training, level 1 plus 2, only on the string task.
So it learned the abstract composition skill in the string world, and now we're seeing if that skill helps it solve countdown problems, even though it never got RL training on countdown composition.
Precisely. Any performance advantage this group shows over the multi-baseline on countdown tasks is evidence that the compositional skill learned on strings has transferred to the arithmetic domain.
Just to be super clear, no model here got RL specifically for level 3 or level 4 countdown problems.
Correct. The RL was purely on the string transformations.
So if this multi-base plus RL model does better on complex countdown, it really suggests the structure of 1 on strings somehow mapped onto the structure of, say, A plus B times C or in arithmetic?
That's exactly the hypothesis being tested. Has it learned a domain general meta skill for sequential nested execution? Hashtag tag 4.2 transfer results on countdown figure 4 analysis.
Okay, so what did figure 4 show? How did these groups perform on the harder, held-out countdown problems, level 3 and 4?
Well, first, observation 1 confirmed the prerequisite. The string base plus RL L1 plus 2 model, the one that knew composition but not arithmetic. It failed completely on countdown, scoring near 0.
Okay, so you definitely need the basic building blocks for the task at hand. Check.
Check. Now for the exciting part, observation 2, which really demonstrates takeaway 3. Transfer succeeded.
How so?
The multi-base plus RL L1 plus 2 model, the one with atomic skills for both, but RL composition only on strings performed significantly better on countdown than the multi-base baseline, which had both atomic skills but no compositional RL.
Significantly better by how much? Let's look at level 3 countdown.
On level 3 countdown problems, the RL enhanced model achieved about 35% accuracy. The multi-base baseline only managed about 17%.
Wow, that's an 18 percentage point improvement. Double the accuracy. From a skill learned in a totally different domain.
It's a substantial jump. It strongly suggests that the model didn't transfer knowledge about, removing vowels or duplicating characters. It transferred the abstract procedural knowledge of how to handle nested dependencies.
The hierarchical reasoning program itself.
That seems to be the most plausible interpretation. The RL training on strings essentially taught the LLM an abstract policy. When faced with nested operations, systematically execute the innermost one, pass the result to the next level out, execute that, and repeat until done. It's a domain-agnostic meta skill.
So when it sees a level 3 countdown problem requiring multiple arithmetic steps, it can apply this learned structural template using its arithmetic atomic skills.
That's the idea. It leverages the general compositional framework learned via RL on strings to better organize and execute the specific arithmetic steps needed for countdown.
This could have big implications.
It really could. It offers a potential explanation for why some generalized RL fine-tuning approaches, like maybe logic RL or others mentioned in the field, seem to improve capabilities across various domains.
How so?
Well, if pre-training gives an LLM strong atomic skills across many areas, basic math, coding, logical steps, language manipulation, then maybe targeted RL training that teaches compositional structure in just one of those areas could unlock improved structured reasoning across all areas where those atomic skills apply. The compositional skill acts as a general reasoning enhancer, hashtag tag 5, challenging the re-ranking illusion.
Okay, this is compelling. But let's circle back to that core debate we started with, the skepticism, the re-ranking illusion argument.
Right, the idea that RL isn't teaching anything fundamentally new, just making the model better at fishing out a correct answer that was already floating around in its potential outputs.
How does the study address that directly? Critics often use the pass-it-back metric to support the re-ranking view, right?
They do. Pass-it K measures the probability of finding at least one correct answer if you let the model generate different possible solutions. The argument goes, if RL is just re-ranking, the performance gap between the base model, say the RFT model, and the RL model should shrink as you increase dollars.
Why would it shrink?
Because if the base model can potentially generate the right answer, even if it's unlikely on the first try, eventually, if you sample enough times, large dollars, it should find it. So the base model's pass-it K catches up to the RL model's pass-it K, suggesting the RL model was just better at finding it sooner.
Okay, so did the researchers look at Passat K?
They did, and this is where takeaway 4 comes in. They dissected Passat K across the different difficulty levels, level 1 through 8, and what they found paints a much more nuanced picture. It critically depends on how hard the task initially is for the base model. Hashtag tag 5.1 Passat K analysis across difficulty.
Use your 5 analysis.
So what did they find on the easy problems? Let's say levels 1 and 2, where the base RFT model already had some capability. On those easy problems, levels 1 to 2, the results actually looked consistent with the re-ranking narrative. The RFT base model already had a reasonably high potential to get the answer right. Maybe not on the first try, but within a few samples. And indeed, as TLAM dollar, the number of samples increased, the performance gap between the RL model and the RFT base model did shrink.
So for easy tasks, the critics might have a point. RL looks like better selection.
It seems plausible for tasks where the base model already has high latent potential, but the story completely flips when you look at the hard problems.
Okay, what happens on hard problems, levels 3 through 6? These are the ones where the RFT base model was scoring near 0 accuracy, even at level 3.
On these genuinely challenging problems where the RFT base model has very low intrinsic potential, low Passat K even for large K, the opposite happens. The performance gap between the RL level 1 plus 2 model and the RFT base model widens substantially as Toulon increases.
Widens. How does that work? Give me an example.
Okay, consider level 5 of 5-function deep nesting. At pass, at 1, just one sample allowed, the RL model is already better than the RFT base, but maybe only by about 4 percentage points.
Okay, small edge.
But now, let the models generate the 124 samples, K1 of 24. The RM model's pass at 124 score climbs significantly, as expected, but the RFT base model score barely budges. The performance gap between them balloons out to approximately 25 percentage points at K1024.
Wait, why does a widening gap challenge the re-ranking idea? Why doesn't the base model catch up?
Because if re-ranking were the whole story, the base model should eventually find the correct answer if it's capable of generating it at all. The widening gap strongly implies that the RL model is generating correct, complex solutions that the RFT base model is simply incapable of producing, no matter how many times you let it try.
The solutions aren't just hiding deep in the base model's potential outputs. They're not there at all for the base model.
That's the inference. If the RFT performance doesn't catch up even with massive sampling, the RL process must have installed something fundamentally new, that compositional meta skill which allows the RL model to construct reasoning traces that are structurally beyond the reach of the base model.
So RL isn't just finding the needle in the haystack better. It's adding new needles to the haystack that the base model never had.
That's a good analogy. It suggests RL genuinely expanded the performance limits, the fundamental reasoning capacity of the model on these hard tasks. The re-ranking illusion seems to be an artifact of studying RL primarily on tasks that were already within the base model's high potential reach.
Okay, the Passat K argument is quite convincing quantitatively, but did they also look qualitatively at how the models were reasoning or perhaps how they were failing? Does the type of mistake change?
Yes, and this provides perhaps the most intuitive evidence for genuine skill acquisition. They did a deep dive into the failure modes, specifically on the challenging level 3 problems. This is takeaway 5.
What kinds of failures were they looking for?
They categorized the errors into a few key types, focusing on the compositional aspect. 1. Ignores composition. This is the most basic failure. The model just doesn't recognize the nested structure at all. It might try to apply one function to the input and stop, or apply them in parallel incorrectly.
Okay, total structural blindness.
Pretty much. 2. Incorrect composition. Here, the model recognizes nesting is needed but gets it wrong. It might misinterpret the order, example, calculate best GSX when it should be GSX, or maybe miss a level of nesting.
So it tries to build the chain but messes up the links or order.
Right. And 3. Atomic error. This is a failure where the model seems to have correctly understood and executed the overall compositional structure, but simply made a mistake executing one of the final basic atomic function steps, like miscalculating func 16 at some point.
So the plan was right, but the low-level execution slipped up.
Exactly. Now, how did the different models distribute their failures across these categories?
Let's start with the RFT base model and the RL level 1 control the ones that didn't learn composition well.
Their failures were overwhelmingly dominated by the high-level structural errors. For both models, ignores composition accounted for over 50% of their mistakes, and incorrect composition accounted for over 35%.
So almost all their errors were fundamental misunderstandings of how to chain the functions. Very few atomic errors.
Precisely. They essentially lacked the systematic plan needed for nested operations. They failed at the strategy level.
Okay, now the punchline. What about the RL Level 2 model? The one trained with RL on compositional problems.
The shift was dramatic, spectacular even. The RL Level 2 model completely eliminated the ignores composition errors, 0%.
Now, completely gone. What about incorrect composition?
That dropped significantly too, down to maybe 10–15%. And where did the majority of its errors go?
It must be the atomic errors.
Exactly. The primary failure mode for the RL Level 2 model shifted massively to atomic error, accounting for about 55% of its fewer overall mistakes.
Okay, this feels incredibly important. What does this shift mean?
It means the RL training didn't just make the model more accurate. It fundamentally changed how the model approaches the problem. It successfully taught the model the architectural requirement of compositionality. The RL model now knows the plan. It knows the order. It knows to handle intermediate results.
So when it fails now, it's not because it misunderstood the structure.
Correct. It fails because it made a slip-up in the low-level execution of one of the basic steps, like misapplying the func-x rule in that specific instance. The high-level compositional program itself seems to have been successfully installed by RL. That's a qualitative transformation in reasoning behavior. #tag 6. Detailed example of behavioral shift.
This distinction is so crucial. Let's really pin it down with a concrete example. The paper appendix, F.2, has a level 3 problem. Can we walk through how the different models attempted it? That should illustrate the failure modes clearly.
Absolutely. It's a great way to see the difference in action. #tag 6.1, the level 3 composition problem.
Okay, so what's the specific level 3 problem?
The task is to predict the output of main solution. And the underlying structure is a 3-function composition. Ishi-AG, which corresponds to func10, func2.
Okay, 3 levels deep. And the input is 6x. It's a Tichikaku. We need to know what functions do.
Right. Innermost function, Kyoji Philly, is func2. Remove vowels, AEB. Middle function, GI, is func13. Duplicate every character in the input string. Outermost function, funger dollars, is func210. Alternate the case of characters. Even indices 0, 2, 4 become lowercase. Odd indices 1, 3, 5 become uppercase.
Okay, remove vowels, then duplicate characters, then alternate case. On the input X, tag 6.2, step-by-step comparison of reasoning. Let's start with the RFT model response. How did it fail? Which category did it fall into?
The RFT model response is a classic example of the ignores composition failure. Looking at its reasoning trace, it takes the input sexdex is sells functog, and it seems to immediately jump to applying one of the functions directly to the input. It looks like it might be attempting func10 alternate case directly on htog.
So it just treated htog as if it were a level 1 problem.
Essentially, yes. Its trace might show something like analyzing HUET for alternate casing, maybe resulting in htog. But the crucial failure is that it completely ignores the fact that it was supposed to first apply func2 and then func14. It never even attempted to parse the sex structure. The trace just stops after applying one function incorrectly.
Okay, total structural failure. What about the RL level 1 model response? This one also failed, but maybe tried harder.
Yes, this response exemplifies the incorrect composition failure. It actually does recognize that func2, remove vowels, is involved, and it executes that first step correctly. It takes sex exclamation dollar and correctly produces the intermediate result htk.
Good start, but where did it go wrong?
It went wrong in the next step. Instead of applying the middle function, func14 duplicate characters, to htk, it seems to have skipped that entirely and jumped straight to applying the outermost function, func10 alternate case, to htk.
So it did func2 sex instead of func10 func2 sex.
Exactly. It applied func10 to htk, which would result in htk. So it attempted composition, got the first step right, but it failed structurally by missing the middle layer of the required 3-step chain. It couldn't execute the full nested plan correctly. Still a high-level compositional failure.
Okay. Now the moment of truth. How did the RL level 2 model response handle this unseen level 3 problem?
This model's trace is where you see the acquired compositional skill shine. It perfectly demonstrates the systematic, step-by-step execution of the func structure.
Walk it through it.
Okay. 1, parse the structure. First, it correctly identifies the full nesting, func2, func14, func2. 2, innermost function. It executes func2k. Removes the vowels, O, E, correct intermediate result.
Perfect first step.
3, middle function. It correctly takes the result, htk, and feeds it as input to the next function, func14. So func14 conjugate is func14 duplicates every character, correct intermediate result.
Perfect second step and transfer.
4, outermost function. It correctly takes that result at HETTKK and feeds it to the final function, func10. So func10, HHTTKK, func10 alternates case, H lower H upper, T lower K upper. Correct final result, HHTTKK.
So it followed the entire three-step compositional plan perfectly.
Exactly. Its reasoning trace shows the correct execution of each nested step, passing the intermediate results correctly. This is the demonstration of the acquired compositional program.
And crucially, even if it had made a tiny mistake in the final alternate casing step, say, it output HHTTKK. How would that failure be categorized?
That would be categorized as an atomic error, because the compositional structure, the parsing, the nesting, the intermediate result passing was executed perfectly. The failure would only be in the final application of the basic func10 rule. This confirms the high-level compositional skill was acquired, even if low-level execution isn't always flawless.
The comparison is incredibly clear. The RFT and non-compositional RL models fail at the high-level strategy. The compositionally trained RL model masters the strategy, and its errors, if any, are typically in the low-level tactics. #outrivalaitric.
So when you put all this evidence together, the findings from this deep dive seem pretty unambiguous. Reinforcement learning, when it's applied with these kinds of explicit compositional incentives, well, it appears to be much more than just a re-ranking tool.
Yeah, it really looks like a genuine mechanism for instilling fundamentally new, generalizable, and even transferable skills in these large language models.
We've walked through the key takeaways, right?
Let's recap them quickly. First, that huge generalization jump performing well on level 6, having only trained on level 2, that proves RL teaches a general principle of composition, not just memorizing examples. That was takeaway 1.
Second, the fact that the RFT model failed so badly, despite seeing perfect compositional traces, shows that compositional data alone isn't enough. The specific optimization mechanism of RL, maybe that binary reward forcing exploration, seems critical for internalizing the process. Takeaway 2.
Right. Third, the success on the countdown task was really striking. It demonstrates the compositional ability isn't just for strings. It acts as a transferable meta skill, letting the model structure its existing basic knowledge in new domains. Takeaway 3.
And fourth, that pass at K analysis decisively challenged the re-ranking illusion, showing it's likely an artifact of studying easy tasks. On hard, novel problems, RL demonstrably expands the model's capabilities beyond what the base model could ever reach, even with infinite sampling. That was takeaway 4.
And finally, takeaway 5, the behavioral shift. Analyzing how the models fail showed RL transforms the errors from high-level structural misunderstandings, ignores incorrect composition, to low-level execution slips, tonic error. It fundamentally changes how the model reasons.
Taken together, these findings make a pretty powerful case for thinking about LLM development differently. It suggests a potentially synergistic strategy. Use pre-training and perhaps supervised fine-tuning, like RFT, to build a strong foundation of diverse atomic skills.
Get the building blocks in place.
Exactly. And then strategically apply RL, specifically using tasks designed with compositional incentives, to teach the model how to assemble those blocks into more complex, generalized reasoning structures.
So the debate really has shifted, hasn't it? It's less about, can RL teach new skills? It seems the answer here is a conditional yes.
The evidence points that way.
The more pressing question now becomes, how should we design RL tasks and reward structures to push this further, to incentivize the learning of even more complex, more generalizable forms of skill composition?
Precisely. If mastering this simple $5 structure unlocks such a significant jump in generalization in this controlled setting, what's next? What is the next compositional structure, maybe involving loops, recursion, conditional logic, planning across longer horizons that LLMs need to master to bridge the gap towards more flexible, human-like problem solving?
That really is the structural challenge ahead for AI development, isn't it? Figuring out the curriculum of composition.
A profound and necessary question for the field, absolutely.
Well, thank you for joining us on the deep dive. We hope this rigorous look into compositional skill acquisition has given you, our listeners, a much deeper framework for understanding how these powerful models might actually be learning and where the frontier truly lies.
Welcome to the deep dive. Today, we're really digging into something fundamental about AI learning.
Yeah, it's a big one.
For the last few years, there's been this intense debate in the LLM world. When we use reinforcement learning, RL, on these big models, is it actually teaching them new cognitive skills? Or is it more like, just polishing things up?
Right, just shuffling around the abilities they already picked up from all that pre-training data.
Exactly. Is it just re-ranking existing reasoning paths?
That's the skeptical take, the re-ranking hypothesis, that RL is like a finishing gloss.
Right. It helps pick the best answer, maybe, from stuff the model could already generate, but doesn't actually make it smarter on harder problems.
Sure.
So our mission in this deep dive is to unpack some fascinating new research. It seems to provide pretty solid evidence that RL can teach genuinely new skills.
And specifically the skill of composition, taking simple things and putting them together in complex ways.
And what makes this study really compelling, I think, is the methodology. They didn't use messy, real-world data.
No, which is key. Real-world data has, contamination issues. You never quite know what the model really learned versus what it just saw before.
So they built this very clean, synthetic framework, like a controlled lab experiment for an LLM.
Allows for real precision. Surgical, almost.
Okay, let's get into that methodology because it's pretty crucial to understanding their findings.
It really is. And it's neat because it actually mirrors ideas from cognitive science about how we learn complex things.
Oh, yeah. How so?
Well, think about learning any complex skill, like, say, cooking a fancy dish. You don't just download the chef's skill.
Right. You learn chopping, sautéing, measuring.
Exactly. You learn basic actions,
Yeah.
the atomic skills, and then you learn to compose them, to sequence them according to a recipe. You integrate them.
You internalize the process.
Precisely. You move from just knowing the steps to actually being able to execute the whole plan smoothly.
Yeah.
This research sets up that kind of learning process for the LLM.
Using this clean test bed, as they call it.
Yep. A deductive reasoning task based on string transformation prediction. Think of it like a very simple, specialized programming language.
Okay, so break that down. What are the components of this language?
So they define two levels. Level 1 is the atomic skill. A single function, like func16x, maybe it reverses part of the string or removes duplicates. It's one self-contained step.
Got it. The basic actions.
The basic actions.
Right.
Then you have the compositional skill level 2 and higher.
And that's where it gets tricky.
That's where it gets tricky. It involves nesting these functions, like func16, func15x. You have to apply one function, then apply another to the result.
And the difficulty just ramps up with more nesting. Level 3 is 3 functions, level 4 is 4.
Exactly. You can precisely control the complexity. It's like giving the model increasingly complex instructions to follow.
And they did something clever with the function names, right? To make sure it was actual learning.
Oh, absolutely critical. The decontamination step. They didn't call them reverse string or anything descriptive.
Because the model might have seen those terms in its training data.
Precisely. It might just, activate some latent knowledge. Instead, they used totally meaningless names. Func16, func03, just arbitrary tags.
So the model had to learn what func16 actually does and how to use it, purely from the examples.
It had to internalize the skill and link it to that specific tag. No shortcuts.
Okay, so they set this up using a Llama 3.18b model, and the training had 2 stages.
2 stages, yeah. Stage 1 was atomic skill acquisition, learning those basic level 1 functions.
How do they teach those?
They use something called rejection fine-tuning, or RFT. You can think of RFT as like super high-quality supervised learning.
Okay.
In this stage, the model could see the function definitions, what func16 actually did, and RFT gave it perfect step-by-step reasoning examples, like showing it the fully worked-out solution.
So it learns the individual tools perfectly.
Learns the mechanics of each tool. Then comes stage 2, compositional skill training.
And this is where the real test happens.
This is it. Now, the function definitions are hidden. The model only sees the tags, like func16, func15x.
Just the recipe, not the instructions for each step.
Exactly. And here they compared 2 approaches. One group continued using RFT, still getting perfect step-by-step reasoning for the composition.
Okay.
The other group used online RL, reinforcement learning. And the RL group got a much simpler signal.
Just right or wrong.
Basically, yeah. A reward of 1 if the final output of the whole composition was correct, 0 if it was wrong. Much less guidance.
And what was the immediate big takeaway from comparing these?
The big thing was that RL training on these level 2 compositions, the 2 function chains, actually taught the model a new skill that generalized.
Generalized how?
It allowed the model to solve new compositions like level 3 or level 4 problems involving 3 or 4 functions that it had absolutely never seen during training.
Even though it was only explicitly trained on level 1 and level 2?
Correct. Which immediately suggests RL is doing something more than just, polishing answers it could already sort of generate. It learned a principle.
Let's put some numbers on that because the contrast is pretty stark, isn't it? What happened if they only train on level 1, the atomic skills?
Performance on level 1 was great, as you'd expect, around 90% accuracy. It mastered the individual tools.
But ask it to combine 3 or 4 tools. Level 3, 4, 5.
Nothing. Complete failure, accuracy close to 0.
Wow. Okay.
It knew the individual steps, but had no clue how to follow the recipe, basically.
But then they add RL training just on level 2, the 2-step compositions.
And suddenly, generalization clicks into place. That level 2 RL training unlocked the ability to tackle problems the model had never encountered.
So what were the numbers for level 3, say?
Performance on unseen level 3 tasks jumped from near 0 up to 30%.
Just from learning 2-step chains.
Just from learning 2-step chains via RL. And level 4 performance went up to about 15%. You learned how to combine things.
Okay, but here's the kicker for me. The RFT model in stage 2 also saw the level 2 compositions, and it got perfect step-by-step guidance on how to solve them. Why didn't it generalize?
That's maybe the most critical finding.
Yeah.
It shows that just seeing compositional data, even with perfect supervision, isn't enough.
Really? Why not? RFT seems like it should be ideal.
Well, RFT encourages the model to imitate the exact path, the specific sequence of tokens in the perfect solution. It's great for learning atomic facts or procedures.
Like memorizing the steps.
Kinda, yeah. But it seems less effective at teaching the model to internalize the underlying plan or the strategy itself.
Whereas RL.
RL forces the model to figure out the plan because it's only rewarded for the final outcome. It has to explore, try different sequences, and learn what strategy leads to success. It learns a more robust policy for planning and executing.
It's incentivized differently.
Totally. The incentive structure matters hugely.
And the results comparing RL level 2 and RFT level 2 prove that point.
Absolutely starkly.
Yeah.
Both trained on the same level 2 compositional data, remember? But the RFT model just failed to generalize.
How badly?
It struggled to get even 15% accuracy on held-out level 2 problems the same difficulty it trained on. And on level 3, forget about it. Never got above 2.6% accuracy.
So the conclusion is you need both. You need the compositional data and the RL incentive.
That seems to be it. Both RL and the compositional incentive structure are essential to get this kind of generalizable compositional skill. RFT, even with perfect data, just couldn't cut it for learning the deeper strategic skill.
It sounds like RFT optimizes for, like, predicting the next token correctly along the path.
Right. While RF optimizes for actually achieving the final goal, solving the problem, it learns the objective function itself.
Okay, this brings us right back to the re-ranking debate. The critics who say RL doesn't teach anything new, it just gets better at finding the right answer that was already lurking somewhere in the model's potential outputs.
The idea that the answer is probably in the top 1,000 guesses the base model makes, and RL just helps it bubble to the top, improving that pass at 1 score.
Right, but this study seems to deliver a pretty strong counter-argument. They call it the re-ranking illusion.
Yeah, they argue that illusion pops up mainly when you evaluate on easy tasks. Tasks where the base model already has a decent chance of getting the right answer if you let it guess enough times.
So they use this metric, pass at K, to probe deeper.
Exactly. For listeners, pass at K just means if you let the model generate different potential solutions, what's the probability that at least one of them is correct?
So if re-ranking was the whole story, you'd expect the base model and the RL model to eventually reach the same maximum performance if you made K large enough, right? The ceiling should be the same.
That's the idea. On easy tasks, that gap might shrink as K increases. But here's the crucial part. They looked at pass at K on the hard compositional problems, levels 3 through 6.
And what happened there?
The exact opposite of the re-ranking prediction. The performance gap between the RL model, trained on L1 plus 2, and the RFT base model didn't shrink as K increased. It widened.
It got bigger.
Substantially bigger.
So wait, letting the RL model guess more times helped it more relative to the base model.
Precisely. Take level 5 problems, for example. At pass at 1, the RL model was maybe 4% better. But when you let both models generate 10,024 attempts, pass at 1024, the gap ballooned to about 25%.
That completely torpedoes the re-ranking idea for these tasks.
It really does. It shows RL isn't just reshuffling existing answers. It's fundamentally expanding the model's capability. It's pushing the performance ceiling higher, enabling it to solve problems the base model simply couldn't, no matter how many guesses it got.
The skill ceiling itself was raised.
Exactly.
And they didn't just look at scores, did they? They looked at how the models were failing.
Yes, the qualitative analysis is super revealing. They looked at the types of errors models made on level 3 problems.
What did the base RFT model typically do wrong?
Its failures were dominated by high-level strategic mistakes. Over half the time, it just ignored composition. It didn't even try to follow the multi-step plan.
Just spat out a single function result or something.
Yeah. And another 35% of its errors were incorrect composition. It tried, but it messed up the order of nesting. It just didn't grasp the compositional logic.
Okay, so fundamental planning failures. What about the RL model?
A total transformation in behavior that ignores composition error. Completely gone. Eliminated.
Wow.
The RL model always understood it had to parse and execute the multi-step plan when faced with a compositional task.
So what was its main failure mode then?
It shifted dramatically. Its primary failure became the lower-level atomic era, which accounted for 55% of its mistakes.
Meaning
Meaning it correctly understood the whole level 3 plan, identified the 3 functions, knew the right order, but then it made a small slip-up executing one of the individual atomic steps, like Func 16.
So it went from failing at the overall strategy to mostly failing at the small tactical execution details.
Precisely. It mastered the hard part, the planning, the composition, and now its errors were happening at a much simpler level.
That sounds like genuine cognitive progress, learning the meta skill of how to structure the solution.
It really does. Like learning the grammar of the problem, not just the vocabulary.
Okay, so if it's a real meta skill, this ability to compose, the big question is, does it transfer?
Does it work outside of this specific string manipulation world?
Right. Can it apply this how to combine things skill to a totally different domain, like math?
They tested exactly that. They took the models trained on string compositions and evaluated them on the countdown task.
Ah, the numbers game. Basic arithmetic operations combined to reach a target number.
Yep. And critically, none of the models got any RL training on countdown itself during that second stage. The transfer had to be zero shot.
So could the string composition expert do math composition?
It could. The RL compositional model, the one trained on strings up to level 2, achieved 35% accuracy on level 3 countdown problems.
And how did that compare to the baseline?
Significantly better. It outperformed the baseline model by over 18%.
That's pretty impressive transfer.
And crucially, that advantage held up even at higher complexity, like level 4 countdown, where the other models just completely fell apart.
So the compositional skill learned in one domain provided a real advantage in a completely different one.
It acted like a general-purpose tool for combining knowledge.
Which suggests we might not need to train models exhaustively on every single complex task variation.
Maybe not. If we can teach them these underlying meta skills, like composition, they might be able to apply them much more broadly.
There's a prerequisite, though, right?
Oh, sure. And it makes sense. The model has to already possess the necessary atomic skills for the new domain.
So for countdown, it needs to know basic addition, subtraction, etc. from its pre-training.
Exactly. Just like it needed to know what Func 16 did for the string task, the compositional skill doesn't magically create knowledge of addition.
It provides the structure, the how-to guide for combining the pieces the model already has.
Perfectly put. It's like a universal instruction manual for assembly.
So stepping back, this research really challenges that pessimistic view, doesn't it? The idea that RL is just surface-level refinement.
It strongly suggests that view might be, well, an artifact of how people were testing things. Maybe looking at tasks that were too easy, or using methods like RFT that don't incentivize strategic learning as effectively.
Right. This study seems to show pretty clearly that RL, if you set it up right with the right kind of compositional challenges,
It teaches genuinely new, robust skills. Skills that generalize and even transfer across domains. It's expanding the model's core problem-solving ability.
not just re-ranking, raising the ceiling.
Raising the ceiling.
So what are the big picture implications here for how we build and train LLMs going forward?
Well, it suggests a potentially powerful strategy, doesn't it? A sort of two-phase approach.
Phase 1.
Build the foundation. Use massive pre-training to stuff the base model full of all the necessary atomic knowledge and skills, facts, language understanding, math, coding primitives, you name it.
Get all the basic tools in the toolbox.
Exactly. Then phase 2, use reinforcement learning, but specifically with incentives designed to reward higher-level compositional thinking.
Like rewarding success on these level 2 or higher complex tasks.
Right. To teach the model those generalizable meta skills, how to use its knowledge effectively to plan and solve complex problems.
And that meta skill could then, hopefully, apply across all the domains the base model already knows.
That's the exciting prospect. You teach it how to think compositionally once, and that ability transfers.
Okay, so that leaves us with a really interesting thought to chew on. If RL can turn these fairly simple, learned string functions into a compositional metaskill that then helps solve math problems, what else could we teach? Think about complex human cognition planning, reasoning by analogy, breaking down really hard problems. These are also built on composing simpler cognitive units.
Right.
Could we, if we were clever enough in designing the right set of atomic skills in pre-training, and then the right kind of high-level compositional RL rewards,
Right.
could we systematically teach an LLM some of those truly complex, human-like cognitive abilities?
That's the million-dollar question, isn't it?
It really changes the game if the answer is yes. Something for you to definitely mull over.